everybody. Today we are going to do the video for the notes for section 8.1.3, which is stretch factors for polynomial functions. Yesterday in section 8.1.2, we learned how to make a graph from the equation, and now today we're going to go the opposite direction. We're going to make an equation from the graph. So our objectives are to be able to write the approximate equation of a polynomial function given the graph, and to be able to write the exact equation for the graphs of polynomial functions given the x-intercepts and one additional point. The success criteria, we will be able to do a quick check at the end of the video, and also we want you to know what the general equation of a polynomial is. Just a snapshot of what we're going to look at today. Remember that if a function is in factored form, we can find the x-intercepts using the zero product property. So as an example, if we're given x plus 4 times x minus 7 equals 0, I can set each one of the factors equal to 0, and I can solve for x. So we get x equals -4 and x equals 7 as the solutions or the zeros or the x-intercepts or the roots of my function. Remember that all those things mean the same thing. To write the equation of a polynomial function from the graph, we need to use those x-intercepts or those zeros of the function. And what we do is we start with those x-intercepts of the function and find the factors. So we work backwards to turn those x-intercepts into factors. And then we multiply them together to find the polynomial function, okay? So for these two, whatever the x-intercepts are, we can turn those into factors. So let's say we had x equals -4 and we have x equals 7 given to us, like in the graph that you see here. If we want to turn those into factors, I'm going to pull this -4 back to the other side by adding it to give me 0 on the right side. And I pull the 7 to the other side and make it x minus 7 to get me 0 on the other side of that one. My factors then are x plus 4 and x minus 7. Let's look at some examples to follow that same idea. So first of all, recall how to solve this. This quadratic equation that we have is factorable. So I make my two sets of parentheses. Remember that what's in the beginning of each parenthesis has to multiply to be x squared, so that gives us x, and the other end has to multiply together to give us a positive 5. So that's going to be a 5 and a 1. Both my signs are going to be positive, so we have x plus 5 and x plus 1. You'll notice that the middle term will end up being a 6x if those were multiplied back together. So from here, I set each one of these equal to 0 using the zero product property, and I solve for x. So x equals -5 and x equals -1. So those are my solutions. So now we're going to work backwards to find a possible equation for the following graph. So when we look at this graph, we can tell what the x-intercepts are. So we can see that this one here is at x equals -3. We can see that this one here is at x equals -1. And we can see that this one here is at x equals 4. So I'm going to start out, first of all, by writing those down. So let's start with the zeros. Remember again, the zeros are the same thing as x-intercepts. So what we have then is x equals -3, x equals -1, and x equals 4. So our next step is to write them as factors. So to write them as factors, I want to get back to having 0 on one side, and I want everything else on the other side. So I'm going to have to add 3 to the other side to get rid of the -3. Here I'm going to have to add 1 to the other side to get 0 on the right. And here I'm going to have to subtract 4 from both sides to get 0 on the right. So my factors now are x plus 3, x plus 1, and x minus 4. Notice as you're looking at the graph some things that we know about this graph as well. Because the graph is starting and leaving from different directions, we know that it's going to be an odd degree. We also can tell that because we have 3 x-intercepts, that it's going to be a third-degree equation. So not only did we figure out it's odd, but we also know that it's going to be the third degree. We know what our 3 factors are going to be. So to write the equation, we write f of x equals, or y equals, x plus 3 times x plus 1 times x minus 4. And that becomes our approximate equation for that graph. You'll notice that we can confirm that this is going to give us a third-degree equation, because in here, if I'm checking the degree, if I multiply this all out and use the distributive property quite a bit, actually, at some point, I'm multiplying together an x times an x times another x, and that's going to give me x to the third. So that's confirming that my degree would be 3 and my highest exponent would be 3. So that's something we can check at that point. Okay. Let's look at an additional example. So let's say that we were given the zeros. It says write an approximate equation given that the zeros are the x-intercepts of the function. We're at x equals 3 halves, x equals 3, and x equals -5. I want to show you how to turn this x equals 3 halves into a factor. Because you may recall, when we factor a quadratic expression, we don't have fractions and factors. Our factors always consist of integers. And so we want to make sure that all of our factors still look the way that we've gotten used to them looking. So when we have something like x equals 3 halves, we don't write that as x minus 3 halves. Instead, we're going to try to get 0 on the right-hand side, but we move one number at a time. In order to get rid of the 2 here and to put the 2 on the other side, I'm going to multiply both sides by 2. As I do that, I get 2x equals 3. Then to get, again, my goal of getting 0 on the right-hand side, I need to move the 3 to the other side. Because it's positive, I'm going to subtract it to move it to the other side. So my factor from the x-intercept of x equals 3 halves, my factor is 2x minus 3. So that's something you may need to practice. So make particular note of that so that we don't write this as x minus 3 halves in our factor. The other ones that we have in x equals 3. So to get 0 on one side and to turn this into a factor, it's going to be x minus 3 equals 0. And our 0 at x equals -5 is going to turn into x plus 5 equals 0. So to write the approximate function that would have these x-intercepts, I would write 2x minus 3 times x minus 3 times x plus 5. And that's the function that would fit those zeros. So I wanted to make sure you saw how to turn x equals 3 halves into a factor. In our next example, we're going to write the equation out for the following graph. And so again, we've got a couple things to make note of here that make this problem a little bit different from the other ones. When we look at the graph in the first place, seeing that it's entering and leaving from the same direction tells us that it's going to be an even degree. If you look at the graphs, let's write that down first of all. We know it's going to be an even degree. We can tell that by looking at the graph. Here's the issue. If you look at the graph, I only see an x-intercept here, an x-intercept here, and an x-intercept here. That's only 3. We set it a 4th degree equation because, again, 3 is not even. So it must be that we need to have a 4th degree equation. So here's what we learned, and you talked about this, or you saw this yesterday in 821 or 812 as well, that if you have if the graph bounces off of the x-axis and goes back up, or if it comes from the bottom and hits the x-axis and bounces away, then we have a double 0 at that point. So we're going to make a note here that there is a double 0 at x equals 2. So what we know now is that we have zeros at x equals -3. We can see that from the graph. We have a 0 at x equals -1. And we have a double 0 at x equals 2. So what that means now when we create a polynomial function, remember that we're going to turn each one of those zeros into factors. So the -3 is going to become x plus 3. The negative 1 is going to become x plus 1. The x equals 2 is going to become x minus 2. Because it's double, we square it. Now again, in order to check to make sure we have our degree right, remember that we would multiply all of this together to determine the degree. And at some point, I'd be multiplying an x times an x times an x squared because of that right there. When I do this, I add my exponents, and at some point, I would have an x to the 4th. All right? So realize that we have that even degree taken care of, and this, in fact, is a 4th degree equation. So now let's talk about whether we have an accurate graph or not. So we're going to check the equation by putting it into our graphic calculator. And we're going to use the window that's at the right, so you can see what the window should be in your calculator. And we want to know if the equation is accurate. So we're going to put that into our calculator. We're going to use this x plus 3 times x plus 1 times x minus 2 squared. I'm going to go over to my calculator here that I have on my smart board. And I've got the equation entered this way. Note how we entered that into our calculator. We can put parentheses around those factors just like we had it written on our paper. So now that I have this, also note the table that you see on the screen. And we're going to look at the graph. And when you look at the graph and compare that to what we saw here being drawn, you can look at the one that's in this picture, we see that it's not stretched quite right. Again, here's a picture of the one we started with. And here's the graph that we came up with. So it's not going down quite as far as we'd like for it to, and the little hump doesn't go up quite as far as we'd like. So it's not quite as accurate as we would want it to be. You'll also notice that the point 116 is on our graph. If we look back at the equation that we have graphed in our calculator and look at the table that you have in the middle of the screen, you notice that the point 116 is not on the graph. Our graph contains the point 18. So this equation isn't quite as accurate as we would like for it to be. So let's talk about how we get an equation that's very accurate, okay? Because we notice that we have a few issues with this one. So we're going to use example 5 to show us how to find that exact equation that fits the points that we know in the graph that we see. So we're going to write a polynomial equation for a function with a graph that bounces off the x-axis at -1, 0, crosses it at 4, 0, and goes through the points -2 and -18. So given the x-intercepts that we're looking at here, we know that we have x equals -1 as one of our zeros, and then it bounces off the graph at that point. So that means that we're going to have a double 0 at x equals -1. We also know that x equals 4 is a 0 of our function or an x-intercept on our graph. So that's what we have to work with. So we know that with a double 0 at x equals -1 and a 0 at x equals 4, that we're going to have a 3rd degree polynomial. So that's where we're headed. That's our goal. So as we write our equation, here's what we have to do. Whenever we're expected to find the exact equation to fit a particular graph, we're going to put an a value. I'll put that in a different color just to make sure it stands out. We're going to put an a out in front that's going to serve as our stretch factor. And that's the value that we need to try to find so that we have the exact equation for the graph that we're looking at. So after that a, now we put in the factors that we know. The 0 that's at -1 becomes x plus 1 as a factor. Because it's a double 0, it has to be squared. The x equals 4, the 0 that we have there, turns into the factor x minus 4. So now we've got sort of a general setup for our equation. We need to find the value of a to know what the exact value is for the equation that will fit all this information that I was presented in the problem. This is where the extra point, -2, -18 comes in. I've got to make sure that my graph is going to hit that point or go through that point. So what we do is this. We're going to substitute in -2 for x and -18 for y. and then we're going to solve to find what the value of a is. So I've got negative 18 equals, here's my a. In place of the x, I'm putting the negative 2. So I've got negative 2 plus 1 squared. And then also in place of this x, I put negative 2. So here's what I've got at this point. As I simplify the right-hand side, negative 2 plus 1 is negative 1. So I've got negative 1 squared. I'll give you a couple intermediate steps here so you can make sure you're following what's happening. And then I've got negative 2 minus 4 gives me negative 6. So to simplify further, negative 1 squared is 1. 1 times negative 6 is negative 6. So now to solve for a, I'm going to divide both sides by negative 6. And I get a value then of a equals 3. So I took negative 18 divided by negative 6, so we got an a value of 3. So what that means is that my exact equation is f of x equals 3 times x plus 1 squared times x minus 4. So with that value of a, we know that we have the exact equation and not just an approximate one. So all the hills and the valleys will go to the right height, and we'll make sure that our equation actually matches what the graph looks like. So to find the degree of a polynomial function that is in factored form, you have to think about what the degree would be if you multiplied it all out. Now this is something that hopefully you've given some thought to in the last couple days, because this is not the first time we're talking about it, finding the degree. So if it's in all multiplied out, the highest exponent is going to give me what my degree is. If it's in factored form, which is what a lot of these equations have been looking like, then what I have to do is I have to add the exponents together from my factors. So let's take a look at some of these. So the polynomial function is in general form, then the degree will be the highest exponent. Find the degree and the leading coefficient of the following. So the first one we're looking at is a polynomial in factored form. So you'll notice that I have, this is x to the first power, this factor has x to the first power, this factor has an x to the first power, and this factor has an x to the first power. Okay? You'll also notice that this coefficient was a 3, this coefficient was a 1, this coefficient was a 2, and this last coefficient was a 1. If I multiply all of that together, 3 times 2 is 6. I get x to the 4th power. So what that tells me is that my degree is 4. That's the highest exponent I'll have in any term. And my leading coefficient is 6. The leading coefficient is the coefficient of the term that contains your degree. Looking at a polynomial in general form, everything's already multiplied out. This is when it's a little bit easier. So the degree here is the highest exponent, which is 5. And the leading coefficient is the coefficient of that term where I got the 5. So that leading coefficient is 4. Now I'd like you to take a look at the math notes for this section. It may be a little bit small on the screen that you're looking at. If it's not too small, if you're able to read it, go ahead and pause the video at this point and read through this. It's also obviously in your textbook, so you can take a look at it in this section in your textbook. What this is explaining is how to write the general equation of a polynomial. And just for an example, this first one that's written here is an example of the general equation for a third degree polynomial. And we write that as f of x equals ax to the third plus bx squared plus cx plus d. So they talk in here further about how to write the general equation for a polynomial of any degree. So again, pause the video so you have time to read through those math notes. Now we're at the point where we'd like to do a quick check. So we'd like to see how we're doing with this material. So you're going to want to pause the video again at this point and try these questions. After you get a chance to try them, then play the video again and we will check your answers. All right, so looking at this quick check, first of all, it says, is the degree of the function even or odd? And then what is the degree? So something that you'll notice is that the function enters from a different direction than it's leaving. So that tells me that it has to be an odd degree. That's how we figure that out. So the fact that it's entering and leaving from opposite directions. That's the key to figuring that out. Okay. Then we want to know what the degree is. So then we have to examine our x-intercepts to figure that out. I see that there is, and let me take away our entering and leaving circles here. I see that there's an x-intercept here at -3. I see that there's an x-intercept here at 0. And it is worth noting that the graph is flattening out at that point. And so we learned in yesterday's lesson that that means that we have a triple 0 where the graph flattens but continues to go through that point. I also see that I have an x-intercept or a 0 over here at 2. So to figure out the degree, I've got 1 at this point, 3 here to contribute to my degree, and 1 here. So that tells me I have a total degree of 5. So now we want to write the equation for this graph that we're looking at. So again, we would like to do the exact equation at this point. So I'm going to start out finding what my zeros are and writing those down. So again, we had a 0 at x equals -3. We have a triple 0 because of the graph flattening out at x equals 0. And we have a 0 at x equals 2. So we're going to start out by writing the factors of that and assembling those into my polynomial equation. Remember that we want to start with an a. We need to start with an a value there. That's going to represent my vertical stretch factor. We'll need to find that after we get our factors all set in place. So the x equals -3 is going to become a factor of x plus 3. The x equals 0 actually becomes a factor of x plus 0, or just x. And I've got 3 of those. So I need to have an exponent of 3 on that x. The x equals 2 becomes a factor of x minus 2. So what we'd like to do now at this point is to find that value of a. So we're going to substitute in another point that we know from our graph. And that's where this point, -2, -30 comes in. So the -30 is going to go in place of the y. A is staying put because that's what I'm going to try to solve for. And -2 is going to go in place of the x. So we've got -2 plus 3. We have a -2 being cubed. And then we have a -2 minus 2. So as we simplify that right-hand side, -2 plus 3 is going to be a 1. -2 cubed is going to be -8. And -2 minus 2 is going to be -4. To further simplify that right-hand side, we've got 1 times -8 times -4 gives me a positive 32. So to solve for a, I'm going to divide by 32. Now I can either reduce that number, that fraction I should say, or I can write it as a decimal as long as it comes out to an exact decimal. So whichever way is easier for you to work with is absolutely fine. My a value could be -15/16. Or if I actually divide that in my calculator, I get -0.9375. So now putting everything together to write the equation, I'm going to have f of x equals, I'll write in that -15/16. And then I have the rest of my factors, which again was x plus 3 times x cubed times x minus 2. Now something to be aware of as well is usually when there's a factor of x like we have in the middle here, that's usually written out in the front. So probably an even better way to write this function would be the -15/16 times x cubed, then put the x plus 3 and the x minus 2. So that's the function, the exact function that fits the graph that we were given. Hopefully you learned today what we are hoping that you learned today, which is trying to write the equation for graphs, working with the x-intercepts and turning them into factors. And this brings us to the end of our video for today. Hopefully you enjoyed it and learned something and took some notes along the way. We'll see you tomorrow.